Dear students, welcome to another day's lecture. Yesterday we talked about principal stresses, principal planes, and um, some students have doubt about how many principal planes are there. You see, there are in all three principal planes. Okay, and similarly there are three principal stresses. You see, and the formula that gives the principal stresses, you see, one is maximum principal stress, that is sigma 1. Here two equations are there in this formula. One is sigma 1, the maximum principal stress, is equal to sigma x minus sigma y by 2 whole square plus square root of sigma x minus sigma y by 2 square plus tau xy square. And whereas the minimum principal stress, that is sigma 2, is same, only that you have to take the negative sign here. Okay, these are two equations, one for sigma 1, that is the maximum principal stress, another for sigma 2, which is the minimum principal stress. And there is another principal stress which is called as maximum shear stress. So this is tau maximum. Tau maximum is given by this formula, square root of sigma x minus sigma y by 2 whole square plus tau xy square. Okay, these are three equations. These are the three equations. Here two equations are there, one with positive sign, one with negative sign, another, this is the third equation. Okay, and then this gives the theta, the formula with theta, that tan theta is 2 tau xy divided by sigma x minus sigma y. See, what is this theta? Theta is the angle of the principal stress, angle that the principal stress makes with the x-axis. Okay, now there are three principal planes, I said. See, one principal plane contains the maximum principal stress. The second principal plane contains minimum principal stress. Third contains maximum shear stress. And how these are oriented? You see, if two planes are perpendicular to each other, okay, so one plane contains the maximum principal stress and the mutually perpendicular thing contains minimum principal stress. And this thing, that maximum shear stress, this plane is at an angle of 45 degrees to these things. Okay, so that is how these principal stresses are there. You see, the derivations of these formulae you must have learned either in applied mechanics or some. Okay, and here in this question, in this subject, elements of machine design, they will not ask you to derive these things because you have already studied. Now only you will use these formulae. Okay, and these notations, no, sometimes may vary. This sigma x, sigma y, this tau xy, these things may vary, but equations are similar. And one more thing I wanted to tell you is, when I am sending quizzes, I am sending the quizzes in via Google Forms. Google Forms cannot take this to the power 2, here to the power 2 and all these things. Instead, they say something is m square is there, it may simply write as m2, but that much you should be able to understand what it is trying to say, because we cannot put exact mathematical equations in Google Forms. Okay, And one more thing I wanted to tell you is, when you are solving multiple choices, what you should do is, you should not only see which is the right one. Sometimes, it so happens there can be more than one right. See, A also can be right, B also can be right, and at the end, you may have A and B. Just by looking the first answer, you should not say this is the answer and check it. Okay. So what is the method is, see, you should see all the four, and if whenever you are in a slightest doubt, what you should see is, you should eliminate which of these things is which of these things to be completely wrong. Eliminate the wrong ones, and finally you will end up with the right answer. That way also you can you should that method also you should use while solving the multiple choice questions. Now, coming to another important topic in machine design is the factor of safety. As you can see here, so many times these questions are asked, okay, about the factor of safety. See, you should be able to define the factor of safety and different considerations when you are selecting the factor of safety for a machine component. Okay, and here this question says, how much should be uh, define the factor of safety for brittle material and for ductile materials. And what do you mean by factor of safety? Enlist four factors on which factor of safety depends. Okay, so now let us see what is factor of safety. Okay, factor of safety, this is a term we often use in machine design. Okay, you see, when you are designing a component, uh, say um, while you are designing a mechanical component, always there are certain areas of uncertainties, such as variation in dimensions, variations and non-uniformity in the material strength, etc. Hence, in order to prevent the failure of the component, designer assuming a value of design stress which is very less as compared to the yield stress or ultimate stress. So the factor of safety is defined as maximum stress to working stress or design stress. You see, uh, okay, let me explain like this. Suppose you are making a bicycle. So how many people normally drive a cycle? One person drives. Okay, so one person means, the maximum what will be is weight. Okay, on an average vehicle, the weight may be 60 kgs. Okay, sometimes a heavy man may sit 80 kgs, or sometimes two people may sit, huh? Then 120 kg. And is it that only two people always travel? No, there can be some times where three people sit, where four people sit, or when they will have a big load of a big bag of wheat or sugar on the cycle, and they are taking it like that. See, we cannot simply say that this cycle, if a 60 kg person is sitting, it will not break, and you design. So you see, now you understand that the load coming upon this cycle is not steady. Huh? We cannot simply say average load is this, so for average I will design. You cannot say. What you should do is, you should design for the worst possible condition. So if it should not break for two people, three people, huh? For five people sitting on the cycle also, you should not break. Okay, so this is one thing. This is uncertainty about load. Okay, and also secondly, uh, that material by which the cycle is made, the rods and all those things, the material it is made, we don't know from which factory it is coming. We don't know for what method they are doing it. Okay, see, though the data books and other people give that yeah, if it is a mild steel, it should have so much strength. If it is medium carbon steel, it should have so much strength. If it is high carbon steel, so much strength. If it is a alloy steel of a particular composition, it should have so much strength. They may give in data books, but exactly the method of manufacturing we don't know. Where it is being produced, we don't know. At that, when the time of manufacturing, what all factors took place, we don't know. So whether internally in the component, whether there are any blowholes or uh, uh, any kind of problems in the crystals, we don't know. Okay, so we don't know about the material properties. We are not very sure that everything that is said mild steel will have the exact same strength. We cannot say. Okay, so there are uncertainties about the material properties. There are uncertainties about the loads also. uh, See, the uncertainties means variations. There may be variations about in the material strength, in the uniformity of the materials, in the material strength, and in environmental conditions. We don't know whether something will be used here in Jargaon or used in Bombay, where the sea coast environment will be there. There will be salt in the air. So many. So see, because of the salt in the air, the things just corroded, most corroded in Bombay compared to Jargaon. Jargaon air is not salty because the sea is not close by, like that. See, the environment conditions also, and we don't know at what temperatures they'll be used. Something may be used at low temperature, something may be used at high temperature. We don't know about various conditions. So because of this, when we, as a designer, we are designing something, we have to be very careful. Okay, so say suppose you are going to say Nasik, you are going for some work. Okay, and you are having, you have, okay, you have booked the ticket. Suppose in the train you have taken the tickets with you, and also you have some extra money with you. Suppose you have 100 rupees. Okay, so um, see, you want to see on the way, you want to buy something. On the train you want to buy something. Okay, will you spend all your money? Huh? The first vendor that he comes, will you spend all your 100 rupees with him? No, you don't know whether further you may need that money. For some other purpose you may need money. For somewhere for going in the rickshaw you may need some money. Okay, you won't spend all the money. You think, no, I don't have 100 rupees. Okay, let me think that I have only 20-30 rupees. That much let me spend, and the remaining things let it be there. We don't know what emergency will come. So at that time I should not be left without money. On the same lines, when a designer is designing, what he will do is he will not think that our material has so much of strength. Okay, so what a designer will do is he will think that my material has much less strength. Okay, if that is having for less strength, he will design. If less strength is he designs, and suddenly due to unforeseen things, some more load comes, or some severe environment it is used in, or anything comes also, it will be able to sustain. Okay, for example, okay, when you come to ductile material. Ductile material, this factor of safety, you see, a ductile material, when does ductile material fail? Okay, I told you before, ductile material, an example of ductile material is mild steel. Okay, and mild steel, if you are using it for any machine component or something, see, what should not happen? It should not yield. It should not yield. So that means what? You see, if it is of length of 100 mm, Okay, how much ever load it comes, that 100 mm should remain as 100 mm. When load is removed, it should come back to 100 mm, and it should never become 100 mm should not be 105 mm or 110 mm. That means what? If it has become 105 mm or 110 mm, that means what? It has yielded. That yielding should not take place. So for a ductile material, when it has yielded, that means in the stress strain diagram, when it is past the yield stress level, that means we consider it that component has failed. So for ductile material, yield stress is the failure stress. That is where it fails. Okay, it need not break into two pieces. Even just a little elongation. Uh, you see, suppose your door is there. Sometimes in winter you see that, because it is made of wood or something, it expands a little, and it is very big, difficult for, and it is difficult for closing, and uh, therefore a little elongation also is not permitted. So what we should do is, in factor of safety, when we that's why we take something called as factor of safety. Okay, again similarly, for a brittle material, when it will fail, we assume, because there is no yielding there, no necking there, so see, it is assumed to fail at ultimate stress, whereas ductile material is assumed to fail at yield stress. So this is the failure. Where it fails, somebody asks you, where ductile material fails, yield stress, it will fail. Where brittle material example, what I told you before, is cast iron. Where cast iron fails, it fails at ultimate stress, because it has no yielding there. Okay, so now factor of safety. So you see, here a definition is not clearly given. I will tell you my definition. You see, you should say a factor of safety. Otherwise, you can write and keep this definition somewhere. Factor of safety is a factor that is considered while designing a machine component, taking into considerations the uncertainties about the material properties, uncertainties in the environment, and uncertainties in uh, loading conditions. That's all. This is the definition. You can use it. This is the factor we are using. This factor, normally what will be the factor? Factor of ductile, say factor is what is this? Factor of safety can be to the order of 3. It can be 5. It can be 2. It can be 1.5, like that. These are the values. Sometimes it can be as high as 10. Okay, normally what we do in our problems here and all is factor of safety of 3. Okay, it depends. For some materials we will take high, some materials we will take low, and we will see how the factor of safety is. Okay, now you see, when somebody says, no, this is the factor of safety, most of the students write these two lines as the definition of factor of safety. Factor of safety is defined as maximum stress to working stress or design stress. You see, I don't consider this to be a good definition. Okay, rather you write the definition that I have given. Okay, now, therefore, now for ductile materials, what is the factor of safety? Factor of safety is given like this: n suffix f. F is for factor of safety, and n is just taken like that. Factor of safety. Nf is yield stress upon working stress or design stress. Working stress means, suppose somebody is uh, working, or some design stress, how much load is coming. Okay, that is the thing. It can be, you can say it is working stress, or you can say it is design stress. So yield stress upon working stress, or yield stress upon design stress. This is the factor of safety for ductile materials. Okay, for brittle materials, the factor of safety is defined as the ultimate stress upon working stress, or ultimate stress upon design stress. Okay. And for shear stress, under shear stress conditions, factor of safety is um, yield shear stress upon design stress. Yield shear stress upon design stress. Okay, this is for um, um, under shear stress conditions. Okay, now let us come to selection of factor of safety. How do you select factor of safety? Selection of factor of safety, see, it depends upon number of considerations such as material, mode of manufacture, type of stresses, general service conditions, and shape of parts. The following parts must be considered. One is reliability of the properties of material and change of these properties during service. Reliability of the properties. How reliable, how dependable are these properties of the material? Are they dependable? Oh, yes, we can say, oh, our material is dependable. Oh, sometimes we say, it is used in salty environment. Will it have the same properties? Or it is used at high temperatures. Will it have the same properties? Uh, we, that we cannot say confidently. Some materials may change their properties at different environments. Okay. Then change of these properties during service. While service, sometimes you see some of the materials rusting away. So rusted away means what? Something is corroded. Why? What happens when corroded? Some of the you see outer surface uh, has rusted and fallen off. That means what? The remaining cross section is reduced. Okay. So in service, actually when you bought it new, it was having so much of cross section. Is it now having the same cross section? No. See, service conditions may change. Service conditions may change. Hmm? Like you know earlier we thought of using it in some way, and afterwards we have changed. The service conditions may change. Okay, depending upon that, now we have to select the factor of safety. Second is reliability of applied load. Applied load means, you see, I told you, in a cycle, how many people are sitting? Two people are sitting, three people. A man sitting on a cycle is a load on the cycle. That is the meaning. Okay, reliability of load. We don't know. We are not so confident about the load that it will come only so much all the time. Then extent of localized stresses. Sometimes machine components may contain localized stresses. If they're not heat treated and removed, okay, then no, these localized stresses also you have to take into consideration. Then certainty is the exact mode of failure, how it fails. If you're not certain, if you have not a full knowledge about the material, then you have to use a larger factor of safety. The extent of simplifying assumptions. Sometimes, most of the cases we simplify the formulae. So because of that also depends. The reliability of test results and accuracy of application of these results to actual machine parts. And see, when we are deciding the strength of some material, we depend upon the test results, how far they are reliable. Then extent of initial stress set up during manufacturing. Again, internal stresses we talked about, and again localized stresses we talked about, and like that initial stresses also can be there. And then the extent of loss of life if failure. That means if a machine component fails, how many people are going to die? You see, suppose you are going on the cycle or motorcycle, something happens and it doesn't go forward. Okay, will there be so much of loss of life? And suppose in an aeroplane you are going and suddenly the engine stops. So there, how many ever are there are going to die. That's all. From that height, if you fall, nobody will be living, surviving. So there, you should be more careful when you are designing an aeroplane, because loss of life is more Whereas here on the road, no, loss of life won't be that much. So that also you should consider, how much of loss of life. Then what is the extent of loss of property? How much loss? Suppose a component fails, how much loss will happen? You can say, this I may lose 100 rupees. Something maybe I may lose 1 lakh rupees. Oh, then you have to be very careful when where a machine component is being used in, in an application where if it fails, it will result into a loss of 1 lakh rupees. Then you have to use greater higher factor of safety. Okay, like that. So loss of life, less loss of life, less loss of property, then use factor of safety is like 2 3, like that. Where more loss of life is there, you may have to use 4 5 6, like that. Okay, the value of factor of safety based on ultimate strength for different materials, types of loads. Okay, so this is about the various factors that we have to consider while selecting of the factor of safety.